This presentation is completely different from the previous two that you heard this morning. David talked about all the potential of high computing efforts, all these things you can do, and all this brand new things and data is coming that's available. And then John talked about all the new data that's come in for liquefaction and the tools that are available and the websites that are available. This presentation is going to say, well, gosh, why can't we do that in structures as well? And so my discussion here, which is really going to be a relatively short one, is just talk about where we are and start that discussion of where should we go. So originally I was going to have a discussion, kind of the whole group. Given the timing, you may want to postpone that or do that by email or a survey. But essentially I want to set the table where we started thinking, yeah, that's right, the structures area is really messed up. You really need to start getting your act together and let's see what can be done. Okay. Yeah, but I think we'll leave that to your discussion.
At the end of this session.
Sounds perfect. Okay, so I'll give you a quick set discussion of what's there, just so you set the table. Talk about some current work that's being done at UCLA with peer support, and then finally we'll talk about different things we could do. And as you might imagine, the wish list and the need list and the opportunity list is way beyond any resources we're likely to have in the short run. But in the long run, we should have a vision that's more than let's just increase the number of data points we have in an Excel spreadsheet. Okay, so there's a little bit of history here. The very first work that was done was actually done at NIST by Andy Taylor, who a lot of you know. He's at KPFF in Seattle. It was actually on a 5.5-inch floppy disk. And there was a manual that came with it. It had about 150 different column tests. It was a great idea. No one had done it before. It was available, and then that was a great start. Then Peer, over really a period of 5 or 6 years, funded us to do work to collect more data, make it available to other people through the database. And that ended up giving a Peer structural performance database. It's called the structural performance database, but it only has columns, which I argue are the most important component, but clearly there's more data there that's available. And then NERI and particularly ACI Committee 369 added some data points, added some calculated values. That database is pretty similar. There's a bunch of local people who have done work. There's used to be one for bridges in Japan by Kawashima, who a lot of you might know. That one's actually disappeared and no one knows where it's gone. And of course, there's some work going on in China as well to put this together. And then there's a bunch of people who have done their own narrowly focused database, and I just listed some there. And often they might have like 100 tests because they're just interested in concrete-filled tubes. So they go and do all the literature. They find all the information on concrete-filled tubes. They find essentially a spreadsheet that has all the properties. And these are incredibly valuable, but you can imagine they proliferate and they're all over the world and they're doing different things. You got to find them for the right place. And of course, NERI Design Safe is also familiar to everyone. That's highly detailed work. The demands are high, the expectations are high, and so the number of tests in there is not amazingly big because the amount of data has to be in there, it has to be high quality and prepared. And then finally, there's some work I'll talk in a second about is some work that's being done at UCLA by Saman Abdullah and John Wallace, and I guess Saman has now moved on. And we pretty much want to continue that work and see what can go to the so-called next generation. Okay, so why these databases? Well, in structural engineering, we deal a lot more with codes and a little less with just the natural environment. So we want to be able to access a lot of tests quickly. We don't want to have to do all this processing. And you can imagine every code, every provision has things about strength and shear strength and stiffness and why damage occurs and when it occurs and for what kind of columns does it occur. And then some people want to actually do the force displacement history and they want to actually model things in their detailed model. And for all that, they're all, even though structures people tend to forget it, they are also probabilistic kind of phenomena, where none of the things we measure, none of the things we model are actually known necessarily all that well. And then there's tons of design provisions have come out of that. So you can imagine ACI when they come up with a new shear model like you did a few years ago, they basically go back to these databases. So, and there's actually a competition on the committee where people come in with 10 or 12 different models, and they look at that database statistically and try to fit who has the best, the best fit. The other thing is I found actually quite helpful is often I want to find some data to look in detail. If I have a big database and I can actually start filtering it and say I want this kind of column, that kind of axial load, I want this level of deformation in it. Oh, here's a test. I can then follow up and go find that data and then do the detailed finite element modeling or other kinds of models. So it's actually helpful just as a pointer to other things. And so the current database was developed pretty much in the late 1990s. It appeared on the web in 2004. It's still getting like 50 citations a year, so people are using it. But the peer structural performance database has not had one single change in the last 20 years. Okay, so limitations. Everyone's doing work, but it's always partial, right? Partial regionally, partial one kind of column, or partial one kind of data set. And then everyone, of course, has the properties that they like. No one's using the same description of even what we talked about when we talk about these properties. So if you take properties from two different data sets, you have to somehow meld them together and translate them to a common format. And obviously, if you don't change your database in 20 years, it turns out you miss data. Who would think? And then one thing I always want to be careful about also is that the people who really need the credit for all this work really need to be the people who have actually done those experiments. And so there's always an issue of, as these databases kind of go from one hand to the other and move around, we need to make sure that the focus is very clear on providing attributions to the people who actually did the work of doing these tests. Okay, so here's the landing page for the structural performance database. It has about 400 tests, and it has all things you would expect if you wanted, for example, to calculate the flexural or shear strength of a column, the geometry, material properties, reinforcing details, exactly how it was tested in terms of how the loads were applied, the axial load, of course. And what was new for that database at the time, and actually is kind of unique still, is that it has a whole digital force displacement history. And the reason that's more or less, not quite unique, but unusual, is that it's very easy for me to read your paper, add a column or a row in a database of properties. It's much harder to get the actual force displacement histories because that means the researcher has to go and find that data, which might be sitting on an account for a student who graduated 2 years ago, and somehow that has to spend the time to spend it to you, so you can put it in a database, and then who knows what credit you're going to get for it. So we have that, but that's always much more effort to get when you want to get the whole digital force displacement history. And then talks about when damage occurs, and then a bunch of comments about what's unknown, what's special about that test. And then, of course, always the references. In fact, the specimen name is always the reference because we want people to go back and always refer back to the work that was actually done to begin with. Okay, so in 2020, Peer provided some funding to Simon and John to add some more tests, and they've added a bunch of them. They even presented a few years ago about that, some more properties, backbone curves, and something which we probably should have done back in 2004, and other people have done since, is to have a bunch of generic computed properties. In other words, so many of the calculations we do as structural engineers are very much determined beforehand. It would be like the ACI flexural strength or something like that, rather than requiring every database user to recalculate all those values. Why not just provide them to them? And then there are other things there, nominal strengths, neutral axis depths. All those things are inputs to structural models, and so they're adding that as well. And also, now that's a little easier to store things, they also have these directories with PDFs of some of the key reports and theses that people want. Okay, and here's an example of additional information they're adding to the tests, the actual backbone curve. So that could be extracted just by looking at the paper and pulling off some of these key points. And you can see on the left side is a brittle column. On the right-hand side is a ductile one. The cycling is not really included in that because that takes more work, and that hasn't been done for so far. But you can imagine if you get good definitions of cracking, yields, et cetera, you can then start comparing specimens across the as certain properties vary. And then similarly, he actually has a spreadsheet format right now, which has the moment curvature results for that particular cross-section. And so the numbers are on the right there, the curves on the left, and you can imagine it's helpful for someone to have already done that calculation for you, because these are, if you know the standard assumptions you're making, then why go ahead and do those calculations again? Okay, so I think the main purpose of this presentation was to say, hey, we're a century behind, or at least a partial century behind. What should we be doing next? And so we're going to come out with a survey of many of you, probably all the attendees here, which are going to provide a bunch of ideas of things we could do, things we could prioritize. Some take more effort, some take less, some are more valuable, some are less valuable. And we want to follow up either with a discussion today, but certainly with a survey later, where we talk about what are all the different things that one could do. And I sat there and wrote down a bunch of them kind of quickly. I hope you have better ideas, because that's the whole point of this, this presentation. Obviously, we always want more data, more data, more data. We want to try to get as much displacement histories, because if you really want to get a model that's going to fit for the ground motions, where now we have we have 50 histories at thousands of locations, we really want to get the actual history, not just some kind of strength. We can scan and get all kinds of information, not only reports, but images and videos, point clouds, if you want to do that at this point. To what extent should we be making it more and more dense information for each test? Do we have to do everything? Can we coordinate this with other people's databases? I find it much more comfortable to tell someone, we have a database, we want to work with you. Can we have a bunch of pointers that go back and forth, rather than can I take your data and just throw it into my database and forget about all the work that you've done. So clearly that's something that we'll probably do no matter what anyone says today, because that coordination is actually important. Or should we say, you know what, we're done with columns. We'll add a little bit more, but we really need to be looking at walls and joints and other things, because those are important. So columns are the most common source of failure in reinforced concrete buildings, but other things, of course, are important as well. Or should we actually say, no, actually, we need to provide tools to allow people to look at this statistically. I think in the geotech world, they do that almost always. We do that rarely. Visualization, analysis, and if we're all going to use OpenSeas, why not just have a little code that actually allows you to duplicate that test, and then you change the properties you want to add whatever material model or different model you want to add. And the other thing is that these are all being used to develop, well, papers for sure, theses for sure, but also code provisions. So should we be actually keeping track of version control and saying, this particular provision was based with that data set, and this provision was based on that data set. And if things change in the future, we can always come back and talk about how things need to be changed, and maybe the code provisions need to change. And again, as I mentioned a few minutes ago, we're going to follow up with a community survey. This is the beginning of a process. We hope we'll generate great ideas. We hope that eventually, as the project gets larger, that will include more people to determine how the next generation database will look.